Math 2414, integration by parts. Example 5, the tabular method. Full disclosure, for those of you who are currently in my class using the second edition of Essential Calculus, Early Transcendentals by James Stewart, I'm surprised that I didn't see this in section 6.1. It may be embedded in the homework assignment as an extension topic, but in some books this is actually taught, the tabular method. And I'll show you what it is and what the motivation behind it is. But before we integrate this guy, I want to remind you what's happened previously so far. And in the first example we did, x sine of x, the integral of x sine of x dx, we used integration by parts once. It was the first example, that makes sense. But two examples later, example 3, we integrated x squared e to the 2x dx, and we ended up using integration by parts twice. The reason was, when we did integration by parts the first time, we called the x squared u, and when we took its derivative it became 2x, but it didn't completely disappear. With a second integration by parts, the 2x became a 2, and therefore it was just a constant, and it wasn't an issue anymore. But we had to use integration by parts twice to basically differentiate this polynomial all the way down to a constant. Now take a look at this one. We're going to integrate x to the 4th cosine of 3x dx. And remember, when you're making choices for the u and the dv to set up the integration by parts technique, you are looking for some things. You're looking for things that you can integrate, and I can integrate either one of these, but you're also looking for things that you could differentiate down to a constant, aka a polynomial. So if we were going to do integration by parts, our clear-cut choice for you, well, it may not be clear, but at some point in the future I hope it would be to let, this is our answer, u equal the polynomial x to the 4th, and dv be the rest of it, cosine of 3x dx, and then go on our merry way. But if we were to do this, then finding du, which is a piece of the integration by parts setup, means that we would take the derivative of this and we would knock it down from a 4th power to a 3rd power. But we wouldn't be out of the woods, because we would have an integral with an x to the 3rd power and a sine. Remember, we got to integrate this. And we'd be back in the same boat as before. So one integration by parts would knock this down from a 4th degree polynomial, to a 3rd degree polynomial. Another one would knock it down to a 2nd, another one down to a 1st degree, and after a 4th integration by parts, it would take it down to a 0 degree polynomial, constant if you will. And then integrating the trig function would be pretty easy. So as you can imagine, especially if you watched the previous 2 videos, it's going to get messy and a lot to keep up with, having to do integration by parts, not twice, not 3 times, but 4 times. However, there is I don't want to call it a gimmick, but there's a way to organize what's going on with successive integration by parts without having to stop and reset every time. Here's my next u dv, here's my next u dv. Excuse me, I wish I'd gotten a drink before I started the video. But there's a way to keep up with it, because in essence what's happening when you do multiple integration by parts, there's one guy that's going to get differentiated repeatedly. It's going to be this polynomial, monomial to be more specific. And there's one guy that's going to get integrated repeatedly, this guy. And even though it would technically require a substitution to integrate, we're going to be able to go through it pretty quickly. Also, every time you do integration by parts, you throw a minus in front of this. So if you throw a minus and throw another minus and then another minus, the signs over there start alternating. So if we keep track of all 3 of those things simultaneously, the u getting differentiated, the dv getting integrated, and the signs alternating, we can actually build the answer without the need to actually keep track of everything. In other words, we can organize the work more efficiently in a table. Now, how do we do this? And when should we do this? The time to do the tabular method is when you're doing integration by parts, and one of your parts is a polynomial that you want to differentiate enough until it becomes a constant. And of course, the other part needs to be easily integrable. So here's how the tabular method works. You're going to set up a table that has 3 columns. The titles of the columns are going to be U, dv, and plus minus. You start, now this is assuming you've already identified already identified u and dv. You start by listing u, which is x to the 4th, dv, which is cosine of 3x, and technically has the dx on it, but that's always going to be there, so we can just not worry about it. And then you start with a plus. So you always start with a plus. And then here's what you do. In the first column, you differentiate until it hits 0. Being a polynomial, it's destined to happen. The derivative of x to the 4th is, and let me draw some partition lines here to separate each row. The derivative of x to the 4th is 4x to the 3rd. The derivative of 4x to the 3rd is 12x squared. The derivative of 12x squared is 24x. And remember, we differentiate until it vanishes, until it becomes a 0. The derivative of 24x is 24. And then we hit the 0. Derivative of 24 is 0. So differentiate the u until it vanishes, so it better be a polynomial. For dv, we integrate the same number of times. Integrate, integrate, integrate. And I just realized I did not leave room for one more row. So if you'll give me 1 second, and if you're wondering, why do I need another row? You'll see in a moment. I'm going to rewrite this so that I have room for another row after that. So give me 1 second here. We'll have 24, we'll have 0, and then we'll have a blank row after it. There's not much that's going to be in the blank row. All right, so differentiate until you get 0, and then throw on one more row. Then integrate the same number of times that you differentiated. And this is where you have to be really focused, especially when your integration invokes a substitution. I'm not going to physically take this cosine 3x to the side and integrate it. If you did, your substitution would result in picking up an extra 1/3. It's like when we integrated the e to the 2x, we picked up an extra 1/2. Anytime you integrate and your substitution's derivative is just a constant, if I did a substitution here, it would be for 3x and its derivative is a constant 3. Then you can just integrate as usual and balance it with the reciprocal of that constant. For example, the integral of cosine is sine, but because of the substitution we would have to pick up an extra 1/3, the reciprocal of the derivative of the inside, if you will. And you can always check it by retaking the derivative. Derivative of sine is cosine, chain rule picks up an extra 3, which would cancel the 1/3 and take us here. But I had to keep integrating the same number of times I differentiated. I would recommend taking this in bits and pieces. The 3x is going to stay the same each time. Every time I integrate, I'm going to pick up an extra 1/3. So another 1/3 will make this a 1/9, and then a 1/27th. 1/81, and then eventually 1/243. And if you need to do a calculator move to keep up with all the 1/3, that's fine. But those are the fractions that we get. Now let's focus on the trig functions. Be very careful when you're integrating, because what you think is positive might be negative and vice versa. For example, the integral of sine is negative cosine. And again, you can take the derivative to check. The integral of negative cosine is negative sine. The integral of negative sine is cosine, and now I'm back to the beginning, and the integral of that is just sine. This is probably the part that would take you the most time, especially when it's trig functions, because you have to keep track of the integration each step. If there's a substitution, it's going to bring in the reciprocal of the derivative of the substitution, and with trig functions, you got to watch out for your pluses and minuses. But it wouldn't be a bad idea to quickly differentiate back up here. Derivative of sine is cosine. I would pick up a 1/3 from the chain rule. Excuse me, I would pick up a 3. 3 times 1/243 is 1/81. The derivative of cosine is a negative sine. Chain rule would pick up an extra 3. 3 times 1 over 81 is 1 over 27, etc., etc., etc. But let's say that you whipped out all of the antiderivatives correctly in this column. The third column is easy. You just alternate plus and minus. Starting with plus, so plus, minus, plus, minus, plus, minus. But you go one row deeper, and that's the reason there's this row here. Plus. All right. So how do we milk our answer out of this? In a phrase, tic-tac-toe. It's not really tic-tac-toe, but the way you build your answer is you start with the very top left corner, x to the fourth, and it's almost like you circled a diagonal tic-tac-toe. You kind of have to make your circles a little bit wiggly in order to capture all the pieces. And then you think of this as a big multiplication problem. In fact, you can think of these as plus ones and minus ones, and just think of this as a multiplication problem. If I multiplied everything in this diagonal, I would get positive 1/3 x to the fourth sine of 3x. I would not just write it in the order that you see it, I would put it in the natural order, positive 1/3 x to the fourth sine of 3x. So 1/3 x to the fourth sine of 3x, and I hope I have room to write this. 1, 2, 3. You know what? I'm not going to have room to write it here, so there will be a forced line break in this answer. All right, and then you just keep going tic-tac-toe until you hit the 0. If we circle the next diagonal, we're going to circle 4x cubed, and you don't have to literally circle them. I'm just doing it for emphasis. 4x cubed, negative 1/9 cosine of 3x, and this negative sign. Again, it's easier if you just go, but I don't want to cross them out. And if I multiply all this, treating this like a negative 1, negative times negative is positive, so it's going to be plus. 1/9 times 4 is 4/9. We have x to the third. And we have cosine of 3x. There's the next piece of our answer. And then you just work your way all the way down. The next diagonal, starting with the 12x cubed, will be 12x cubed times 1/27 sine of 3x times positive 1. Again, the diagonals are a little wonky, but just diagonal. And if we multiply all that, let's start with the signs, S-I-G-N. Negative times positive is negative, so we'll start writing that part of the answer here. Let's go to the constants. We have 12 times 1 over 27. Now 12 times 1 over 27 is 12 over 27, but that will reduce by 3 to give you 4 over 9. So minus 4/9. Let's pick up our x's. We have an x squared. You'll notice that the x's are decreasing in power. That's the nature of differentiating it over and over. And then we have sine of 3x. And then, let's go back to red. Starting with the 24x and going down the diagonal. 24x, 1 over 81 times cosine of 3x times negative 1. And let's see, that's going to be negative, positive times negative. Our constant is going to be 24 over 81, but that will reduce by 3. 24 reduces by 3 to give 8. 81 reduces by 3 to give 27. So our coefficient is 8 over 27. Our x is to the first power. And we have cosine of 3x. And then the last one we'll put in green. And it'll be the last one because after this we would multiply by 0 and everything would disappear. So last diagonal is 24, 1 over 243 sine of 3x, and then positive. So if we keep track of all that, positive times positive times positive is positive. Our coefficient will be 24 times 1 over 243, which is 24 over 243. That will reduce by 3. That will give me 8 over 81. So our coefficient is 8 over 81. Our x's, there are no x's. We differentiated them away. And then the trig function is sine of 3x. And of course, being an indefinite integral, plus c. So is it a long answer? Well, yeah, of course it is. Because I mentioned, or we figured out at the beginning, that as an integration by parts problem, it would require 4 integration by parts. So you would pick up a product and then 4 more integrals to do. There's the product, here's the 4 integrals, and of course the constant at the end. Must you do the tabular method? Of course not. But the purpose of it is to keep up with all the derivatives, all the integrals, and all the signs when you have to do integration by parts over and over again. The thing that suggests to do it is one of your parts of the multiplication problem, is a polynomial, but the power is high enough so that it would take a lot of derivatives for it to eventually zero out. Set up the derivatives, set up the antiderivatives, be very careful, especially when they're trig functions. Set up the alternating signs starting with plus, and then you just go tic-tac-toe all the way down, and by the time you get to the 0, you can stop because 0 times anything is 0. And again, you can do this without the tabular method. It's just an alternate technique for organizing all of your work. I challenge you to try to do this problem without the tabular method in order to appreciate how well it organizes all of your work.